And we'll continue on with the bones here. And a couple things now. Last class, we did talk about bone formation and bone resorption. So obviously, we learned what cells are going to help to build the bone, and then what cells help to kind of tear down the bone matrix there. So there's 4 cell types, because again, we're dealing with connective tissue. And if you remember the recipe for connective tissue, it's made up of 3 things, okay? Cells, protein fibers, and ground substance. The latter 2 items, the protein fibers and the ground substance, that's your extracellular material. So now we learned about, all right, what the cells are in our bone tissue. And we saw what they do and how they help contribute and make the organic matrix, all right, the osteoid. And then we saw what happens, that's with bone formation. And then we talked about a little bit about who's responsible for bone resorption. Those are the osteoclasts. So we're going to start to climb into some of the microscopic, I can't talk tonight, some of the microscopic anatomy of our bone tissue here. All right, so we're going to start off with compact bone. And some of this will look familiar to you because we talked about it back when we were going over the connective tissue portion in lab. So you might have heard, and this term looks familiar, I hope, to you folks, and that's the osteon. All right, also known as the Haversian systems. But understand that the osteon, yes, from an anatomical view, it's a small cylindrical structure. To me, it reminds me of a wedding cake. You know, you have all those little layers there, the lamellae. Okay, and then when you pull them apart, it looks like you're stacking up a wedding cake. I'll show you what I mean by that. I got a picture for you I'll show. Okay, but the osteons anatomically, all right, are going to be the most basic functional unit that we're going to see in, yes, mature compact bone. Okay, so it's going to kind of look like a bullseye target. And we're going to see these osteons, all right, these cylindrical structures, they're going to have a parallel configuration to the diaphysis of the bone. So if you recall from the previous class, the diaphysis is the shaft of our long bone. And also to recall, compact bone is going to be more so on the external portion of whatever bone you're talking about. And then just internal to that, that's where we'll see the spongy bone. So we're going to go through some of these components of the osteon right now. Okay, so again, this should be a little bit of a review for you. So you can kind of just set yourself on autopilot, but still pay close attention. All right, so at the center of our osteon, we have a hole, and that's our central canal. Remember when I was saying how bone is highly vascularized? So you got blood vessels that run through it, and you have quite a bit of sensory neurons. Well, it's in these central canals, also known as the Haversian canal, but in these central canals, that's where we're going to see a lot of our blood vessels and our sensory nerves. And they're going to run all throughout. Okay, so again, because as you know, the blood vessels are going to supply the nutrients for, all right, our bone connective tissue. So around the central canal, we're going to have rings. So if you've ever seen a tree cut down, if you look at the stump there, you'll see much like a tree, right? The tree has rings for every year of growth, right? Well, our bone connective tissue also has rings, and it's not correlated to every year of growth, so it doesn't work like that. But there are these rings that surround the central canal, and it's really cool because, all right, these rings are the bone matrix, right? But you can see in these concentric lamellae, all right, the collagen fibers, and this is really important, all right, they're oriented at 90 degrees from the previous and the next lamellae. Okay, so here's your central canal, and then you got a ring that goes around it like this, and then you got another ring that goes around it like that, and then a third ring, fourth, fifth, sixth, we'll keep going. Okay, but the collagen fibers are going to be oriented at 90 degrees from the previous ring or the next ring. That's a horrible picture. I got a much better drawing for you, okay? My computer does not afford me the ability to draw very well. But so keep that in mind. So each concentric lamellae, their collagen fibers are going to be positioned at 90 degrees, all right, in compare or perpendicular to the ring before it and the ring after it. And so that is going to give bone, all right, a lot of its strength and its resiliency, its ability to bend a little bit, that flexibility. So it adds to the tensile strength, right, with the resilience there, because we are dealing with collagen fibers, and that's part of the organic matrix, and the organic matrix gives bone what little flexibility it has. But also because, again, collagen fibers are very strong, they're going to give bone some of its compressive and its rigidity, okay, in comparison to the other connective tissues that we've talked about. So within our bone connective tissue, we've already seen our osteocytes, okay? Those are the mature bone cells that decided to seal themselves up in the bone matrix, right? And they live in those studio apartments, the lacuna, and they're the one that maintains the bone matrix. So if there's any changes, it detects stresses in the bone, increase or decrease in stress. Okay, so if we get an increase in the stress on the bone, the osteocytes will start to trigger new bone formation. And you'll notice, all right, in the lacunae, okay, this little chamber here, you'll have these little lines that spread out from one lacunae to the next. So you'll have some that go over here, and then there'll be another lacunae. Okay, on our micrograph, all right, it looked like these little black lines. And those are called cannuliculi. And they're these small channels, tunnels here, that are going to go from one lacuna to a lacuna that's close by. And so basically, it allows the osteocytes to communicate to one another. All right, and so you'll see this all the way towards the central canal. So as the blood vessels are carrying nutrients, okay, from the central canal and the blood vessels there to adjacent close by lacuna, right, where you'll have some osteocytes, well, then those osteocytes can share, right, nutrients, respiratory gases, minerals, waste products, right? It can share it with other osteocytes. So it's almost kind of like a chain kind of deal going on. So if you see here, let me zoom in. All right. Here's a regular microscopic picture here, and you can see the black dots there. At the center here, there's our central canal. That's where our blood vessels and nerves are going to be. And then you've got the lacuna scattered all around, all right, with the osteocytes inside of them. And so you see all these little black lines, okay, that are coming from the lacuna. Those are the cannuliculi. And so they'll connect to adjacent close by lacuna, and it allows the osteocytes that are close to the central canal, and allows them to share nutrients to some of the osteocytes further away. So it helps them maintain, so they can exchange gases with one another, nutrients and waste products and all that. So here's a nice, real close up micrograph here. Okay, so you can see here at the center, we've got our blood vessels here, some of the lacuna close by. You can see we have these nice concentric rings, all right, going around the central canal. That's our compact bone. Okay, and then here you can see a nice micrograph here of the red bone marrow where the spongy bone is located. All right, so we talked about the central canals, and those run parallel to the diaphysis. Well, guess what? You've got another set of canals, which are called Volkmann canals, or also known as perforating canals. Well, these canals will now go perpendicular to the central canals. Okay, so here is the diaphysis of our bone. So the central canals go this way, whereas the Volkmann or the perforating canals go perpendicular. So as you can see, there's this huge kind of network inside compact bone that is going to allow, right, for the movement of these nutrients, these wastes, for blood, for nerves. So not only do you have nerves in the central canal, you also have nerves and blood vessels in our perforating canals. And so they allow, all right, different osteons, okay, to connect to different central canals. Pretty neat. All right, so we learned about our concentric lamellae, and those are the rings that go around the central canal. We've got two other types of lamellae that I want to discuss with you. Okay, the external and the internal lamellae. So the external is going to be it's going to be found just inside or internal to the periosteum. So that's going to be like this kind of big ring structure on the outer edges of our compact bone. Then we've got another set of lamellae called internal lamellae, right? And those are going to be also internal, but not to the periosteum, to the endosteum. Remember, the periosteum is the covering to the bone. The endosteum is the lining that we see along the medullary cavity there. And so both of these lamellae are going to run the entire circumference of the bone. So I hope you remember what circumference is. That's going to be the complete, like if we're holding on to, here's a bone, long bone here. Okay, the circumference is all the thickness, okay, from here to here, all the way around. And then the last type of lamellae is called the interstitial lamellae. Okay, and these interstitial lamellae are incomplete looking lamellae because a lot of times, and it really depends on what's going on with the history of the bone, all right, but what we'll see is, all right, we're going to see in between some of the osteons, all right, we'll see partially existing osteons. And all that has to do with, you know, bone growth, formation, and resorption. So let's zoom in here and take a peek. Okay, so a couple things. Here is our osteon. All right, now what we're doing is we're now just extending the osteon upwards and outwards, right, from each, I can't talk today, from each lamellae here, okay? So if you notice, it looks kind of like a wedding cake. And in the center here in the central canal, all right, that's where we'll see our blood vessels and nerves. And then these black lines that you're noticing here, that's supposed to be, all right, the collagen fibers. And notice how this layer of collagen fibers is perpendicular or 90 degrees to this layer. Okay, so 45 and 45 is 90. So they're going to be perpendicular to one another. All right, so here's our complete osteon. All right, so you have your concentric lamellae going around here. Okay, and then you'll notice we have this huge circumferential lamellae, one big, long, all right, complete circle. That's going to be on the external portion there, okay, just deep to the periosteum. And then when we go on the inside here, okay, here's our endosteum. Then you can see we have our internal circumferential lamellae here on the inside. Then you'll have partial lamellae here throughout, right, where we've had, and that's the interstitial lamellae. That's where we used to have an osteon, but part of it got resorbed for whatever reason. As the bone was growing, if the bone was damaged, if there's been some stresses detected, and so we had to kind of change things up. All right, so you can see here, right, here's the central canal, and then we have our perforating or Volkmann canals that can connect different central canals. And so again, this allows for a lot of blood vessels to travel all throughout, and for our neurons or our nerves to travel all throughout. Here's our nice nutrient foramen where everything enters into the bone. All right, and then you can see the periosteum on the outside with the Sharpie fibers or the perforating fibers holding the periosteum onto the compact bone. Here's that intercellular layer, and then we have our fibrous layer. So this picture here shows us quite a bit. So if you feel pretty comfortable with this picture, then you're going to have a pretty decent understanding of the microscopic anatomy of bone. All right, here's our wedding cake. Over here, you can see how the collagen fibers are oriented to one another. Then you can see with our concentric lamellae here surrounding the central canal here with the blood vessels and the nerve. With our scattered about, all right, lacuna with the osteocytes living inside, with the canaliculi extending from one lacuna to an adjacent one. So if you look closer here, you can see a pretty good appearance here of the osteocyte. And so it has these processes extending off of the main body of the osteocyte, and those processes will be found in the lacuna, and that's what allows these cells to share nutrients, tissues, minerals, gases with one another. All right, so we talk about compact bone. Let's not forget our spongy bone. We really don't spend a lot of time on spongy bone. We spend a lot more time on the compact bone, but we have to talk about both. So spongy bone, also known as cancellous or trabecular bone, right, has this scaffolding type of construction to it called trabeculae, right, often described as like a lattice-like type of configuration. And so that's what kind of creates the holes that give spongy bone its spongy appearance there. And so in those spaces, that's where the bone marrow is going to reside. And believe it or not, this trabecular configuration, okay, this lattice work here, right, allows the bone, the overall bone itself, right, to resist multi-directional stresses. So it does add, even though compact bone adds a lot to the resistance of stresses, this trabecular type of configuration also will help in offering help to resist stresses also. So we'll see here in the spongy bone, we do have some lamellae here, right? We call that parallel lamellae, right? And that's again going to be similar. There's no osteons in spongy bone, right? But it will have almost an appearance very similar to compact bone. So in the parallel lamellae, it'll be made up of that bone matrix, right? You'll also have osteocytes that reside in the lacuna. And from the lacuna, you'll have the canaliculi kind of spreading out. So here you can see, here's a trabecular structure, okay? And so you'll see throughout, you'll have, let me click on this. So here's all that trabecular scaffolding all throughout this lattice work. So you have these spaces here, and that's where we're going to find the bone marrow in between the spaces here of the trabecula. And then if we cut into one of our trabecula, you can see on the inside, all right, we're going to have our lamellae here, the parallel lamellae that are running around. But we'll see a similar site. We'll see the osteocytes have sealed themselves off in the bone matrix in the lacuna. And then they have their little canaliculi extending from one lacuna to the next. So the same type of scenario occurs, all right? Our osteocytes will share nutrients with one another and exchange gases and waste with one another. And then you can notice here, all right, zoom in a little bit. Here's our endosteum. Remember what we said, the endosteum is the lining of the internal portion of the bone there, the medullary cavity. And it's made up of a single cell layer. Okay, so here's some osteoclasts, and then you also have some osteoblasts around here too. Because again, we can remodel the bone, right? We can add to the bone if the bone is growing. All right, let's take a break from talking about bone. All right, remember we're with the skeletal system, all right, the bone is not the only tissue that we need to discuss. We need to talk about cartilage. We briefly talked about ligaments and tendons and bone marrow. So there's other tissues involved. But I want to take the time to talk to you about cartilage because cartilage is going to play a role. Because remember we said there's two types of cartilage in the skeleton. You have our hyaline cartilage and our fibrocartilage. So I want to start talking about the hyaline cartilage because we're going to start to move into, all right, the formation of bone tissue in the fetus. So in order to do that, we need to discuss, all right, hyaline cartilage. So again, hyaline cartilage is a supporting connective tissue. So it's going to have cells and it's going to also have extracellular matrix. So the cells are similar to what we saw with the bone cells. Okay, you have got a mature bone cell, we call that an osteocyte. Well, with our cartilage, we call it a chondrocyte. Right, then you have the more immature bone cell that would make bone, those are the osteoblasts. Okay, well, in our cartilage, we have chondroblasts. So same type of scenario, right? In the hyaline cartilage, we have cells that are going to produce the extracellular matrix, right? And so the extracellular matrix is going to be made up of protein fibers, predominantly collagen protein fibers. All right, we're also going to see some ground substance, proteoglycans are going to be located predominantly there, in a bunch of water, right? So same scenario happens to cartilage as what we saw with the bone. Okay, the cartilage cells are going to produce the extracellular matrix, the cartilage matrix, and then it basically seals itself off or embeds itself. Okay, now important to understand, we were not going to see calcium in the cartilage matrix. And the easiest way for me to kind of explain that to you, all right, calcium is good in bone matrix. It's good because it helps the bone harden. Remember, our bone matrix, the osteoids, like wet cement. Okay, so when we add some calcium and phosphate to it, that causes the hardening. There's more to it. We already talked about that process there. But see, calcium, we don't want calcium, all right, in our hyaline cartilage matrix, because that is going to kill the matrix for right now. And I'll explain that to you in a moment, okay? So as long as we don't have calcium, all right, our cartilage matrix is going to be nice and flexible, much more bendy than bone, all right? And it'll have some resiliency. A lot of that is due to because we have a higher percentage of water there in our ground substance, so we'll see more flexibility. So of course, cartilage, hyaline cartilage, is a great shock absorber. It's real smooth, so it helps to reduce frictions, and it's highly compressible. But two things you need to understand about cartilage. One, mature cartilage is avascular and no nerves. So if you damage hyaline cartilage, you won't feel it. If you damage fibrocartilage, you won't feel it, right? Because it's not innervated, no nerves. All right, so the cells that make the cartilage matrix are called chondroblasts. They'll seal themselves off in the matrix. When that happens, they convert over into chondrocytes, and they do the same thing that the bone cells did. All right, they're going to live in the lacuna, and they're going to maintain the matrix. So we saw it with the bone tissue. Now we're going to see it with our cartilage tissue. Bone tissue, all right, had the periosteum. Hyaline cartilage has perichondrium, okay, that dense, irregular connective tissue. Now with cartilage, it helps the cartilage maintain its shape. It's helpful. The periosteum doesn't do that, okay, because bone is very rigid and it doesn't need help from the periosteum. All right, but with our hyaline cartilage, the perichondrium helps the cartilage to maintain its shape. So table 7.1 here, you can see some of the characteristics when we're comparing bone tissue, all right, to hyaline cartilage tissue. You can see some of the similarities, all right? Cells that form the matrix, they both have blast in the name. So when we're talking about bone tissue, it's osteoblast. When we're talking about the cartilage tissue, it's chondroblasts. And when both of them seal themselves off in the matrix and mature, okay, then they're upgraded to osteocytes in bone and chondrocytes in cartilage. Now, here's where things get different, okay? Yes, in bone matrix, calcium is present. It's part of the hydroxyapatite, those bone salts. And we want them there because it helps to harden the matrix, gives bone that rigidity. Okay. But we don't want to see it in the hyaline cartilage, and I'll tell you why later on. Okay. But right now, we will not have calcium in the hyaline cartilage. Bone is highly vascularized and it is innervated by nerves. Okay, so quite a bit we'll see in bone connective tissue, but in hyaline connective tissue, hyaline cartilage connective tissue, excuse me, it is avascular for mature cartilage, All right, we're going to move into now the growth of the skeletal system. And before I get into that, okay, I need to talk about how cartilage grows, because we're going to then transition into what happens when you're a fetus and you start to take on the humanoid form, and how you start off with a cartilage model, and then how that model converts from cartilage into bone. So we're going to get into that. So first, we need to talk about cartilage growth. And so this is going to occur, all right, early on in your development. All right, within the first couple of months, you will start to see, all right, the cartilage growth occurring. So we need to define, there's two ways that cartilage grows. One is in length and the other is in width. So I like to compare it to a tree. When a tree grows taller, it grows taller in length, right? And so as cartilage grows that way, that is interstitial growth. This occurs on the inside of cartilage. Okay, the other type of grow is the width. So also like a tree, okay, when you're looking at the stem, I was going to say the stem of a tree, the trunk of the tree, you'll notice young trees usually have a smaller trunk. Okay, and as that tree starts to grow and get older and older, the trunk expands and gets bigger and bigger and thicker. Okay, so it's going to grow in width. Well, cartilage, same thing, right? When it grows in width, it's going to get bigger and bigger. We call that oppositional growth. And that occurs on the outside edge of the cartilage. So how I remember the difference between oppositional and interstitial is, interstitial occurs on the inside. Oppositional is on the edge. All right, so I'm going to take you through both of these types of growth. So I'm going to walk you through. I'm going to tell you a story. So we're going to start off with interstitial growth. And we're going to learn what happens during interstitial growth. So I'll show you this picture here. I'm going to go back and forth. Okay, so we're going to start with interstitial. So we're going to be on the inside of the cartilage. This is the outside, okay, or the outer edge near the perichondrium, but now we're going to be on the inside. So we're going to start off with interstitial growth. And so we have our chondrocyte here, just chilling out. And so that chondrocyte, one day, it's living in its lacuna. I compare the lacuna to a studio apartment. It's like a one-room apartment. So it's living in its lacuna one day, and it decides, I'm going to divide. So where there was one of me, I'm going to make two of me. So the lacuna, the chondrocyte starts to divide. And so where there was one cell living in the lacuna, now you have two cells. Well, guess what? That lacuna is not big enough. That studio apartment just got a heck of a lot smaller. Now there's two people living in that studio apartment. So once we have two cells there, we call those chondroblasts. Okay, so let me go back to this. We'll do step by step. So we start off with the chondrocyte, and it decides to divide. That's step one. When it does divide, now we have two cells. Both are chondroblasts. Unfortunately, they live in the same studio apartment. That ain't going to work. So what they will both do is they're going to make their own studio apartment. So to do that, each chondroblast is going to produce, all right, new cartilage matrix. And as they do that, they push away from each other because they're putting the matrix all around them. They're secreting it 360 degrees everywhere. And so one cell's doing it, the other cell's doing it, and so they're pushing each other away. So once they have officially pushed themselves apart from one another and they have their own lacuna, now they go back to being a chondrocyte. And that's how cartilage grows interstitially. So let's see the picture. This one's easy. Okay, so here's the cell. It's now divided, and we have two cells living in the same lacuna, but they're both chondroblasts. So now they want to get away from each other. They want their own studio apartment. So what do? They each start to produce, right, that new cartilage matrix, and they start to push away from each other. They push away until eventually they have now created their own individual lacuna. They're by themselves, and now they are a chondrocyte. And then they can divide again, and this whole process starts over. So this is how, right, how the tissue, how cartilage grows internally or interstitially. Now we're going to look at oppositional growth, and that occurs on the outer edge. Similar type of situation, but now we're going to deal with the perichondrium. So oppositional growth, we're going to see stem cells that live in the perichondrium, much like how we saw you had stem cells in the periosteum. Remember those osteoprogenitor cells? Okay, and what they would do, they would convert into an osteoblast and they'd start producing bone matrix. Okay, so what we're going to see here with our stem cells in the perichondrium, they're going to undergo cell division. Right, and where we had one stem cell, now we have two new cells. One is going to be a committed cell, which will then be a chondroblast, and the other will be an undifferentiated stem cell to divide again. So enough about the stem cells. With our new formed chondroblast, what does that chondroblast do? Blasts build. So chondroblasts are going to produce new bone matrix, but this occurs at the edge of the old cartilage. So what does that do? It pushes that cartilage away. So it expands the outer portion of the cartilage there. So those chondroblasts are going to push apart. And as they push apart, they become chondrocytes. I got pictures. Always got pictures. Okay, so here's what we're seeing with oppositional growth. Okay, you have your stem cells that live in the perichondrium. And so those stem cells are going to divide and produce, right, a new undifferentiated stem cell and a chondroblast. Okay, so with that chondroblast, we'll start to see the chondroblast doing what it does best. And that's going to be to produce, right, new cartilage matrix at the edge of our cartilage. And as a result of that, that pushes those chondroblasts away from each other. And so as they start to, you can see this perfect example. See how these two guys are in close proximity? Okay, so they're going to produce that new cartilage matrix. And so it pushes them away from each other. And that's what we see here. And so once they've pushed away, then they convert into a chondrocyte, which will still be secreting that cartilage matrix there. And so this is how the cartilage gets wider, how like a tree trunk gets thicker. But this occurs at the periphery there. That's oppositional growth. All right, so why is this important? Well, we need to make, all right, our bone, we need to make our skeleton. But how your body does it is first, it makes a cartilage model. And so we start this early on during the embryological development. First trimester, this is going on. And so we'll see that both of these types of growth are going to occur at the same time. And so as that cartilage ages, that's when we start to see that cartilage get harder. All right. And what we'll see, interstitial growth will decline rapidly. All right. We will still see continued growth, all right, appositionally. So it's not the bones, all right, or the future bones won't get any longer, but they'll start to thicken up a little bit. So keep in mind, what did I say? With mature cartilage, all right, we are going to see, all right, the overall growth eventually stop, right? Only when injury occurs will we see further growth. But we will see now that that tissue has become avascular. That's when it is fully matured. Because we're going to talk about immature cartilage here. And so you need to keep in mind that that immature cartilage has blood vessels. It's vascularized. Only when it becomes mature is it avascular. All right, so now let's talk about bone formation. Because I just told you how we got our cartilage model. So we're going to start to cause, all right, the bone formation to occur as you're developing as a fetus here. So this term is called ossification or osteogenesis. Osteogenesis is new bone growth. So I've seen this asked on a test. When does this start? It starts between the 8th and 12th weeks. That's when our bones that were cartilage will start to ossify. We'll start to convert over into bone tissue. And now that's what we're going to talk about. And this goes on, all right, through your childhood development and adolescence. If you're not exactly sure what adolescence is, that's going to include teenage years and early 20s. So there's two ways that this ossification occurs. What we call intramembranous and endochondral ossification. Those are the two ways that we get ossification. So we're going to talk about both. We're going to start off with the intramembranous because that's a little bit easier to understand. Okay, so we call it intramembranous because right? This is going to occur within a membrane. And so we're going to see it a lot in your skull and quite a bit throughout your axial skeleton, right? Some of the facial bones. Don't ask me why the central part of your clavicle, all right, undergoes intramembranous ossification, and then how the distal and proximal portions of the clavicle undergo endochondral. It's just one of those funny things. Okay, but you want to know where this type of ossification occurs. So in your cranial bones, the flat bones of your skull, some of the facial bones, your jaw, your mandible, okay, and then the central part of the clavicle. So let's go back to story time. I'm going to walk you through, there's only 4 steps for intramembranous ossification. So I'm going to do one step, show you a picture, then advance on to the second step, show you a picture of that. All right. So you're developing, you're minding your own business, you're developing, it's week 6, 7, then we start to get into the 8th week. And all of a sudden, okay, during the 8th week, you start to see these ossification centers just start to pop up in these areas where there's thickened stem cell or mesenchyme tissue. Keep in mind, mesenchyme tissue is where all connective tissue comes from, okay? So in these ossification centers, all right, our osteoprogenitor cells, all right, get derived from that mesenchyme tissue. So we know what the osteoprogenitor cells do. So they'll convert into osteoblasts. And what do osteoblasts do? They build bone. But how do they do it? They synthesize and secrete the osteoid, the wet cement. So that's what happens in step 1. That's what we'll see here. Okay, so we get into the 8th week. you have all this mesenchyme tissue all around, then you get to see these pockets here, right, of where this mesenchyme tissue is located. And these osteoprogenitor cells start to produce osteoblasts. And the osteoblasts start to secrete the osteoid. All right, proteoglycans, glycoproteins, collagen fibers, all right, that wet cement. And so we start to see these pockets start to occur. All right, so during this time, that osteoid, that wet cement, will undergo the drying process, or what we call calcification. What is that? That's when our bone salts, those calcium salts, infiltrate the area and start to sprinkle themselves along the osteoid, the collagen fibers, and it starts to crystallize and harden. And so those osteoblasts now are trapped within that hardened matrix, and they convert into osteocytes. So that's step 2. Our wet cement starts to dry. And so that's what we see here. Okay, so we have our osteoblasts. They've been secreting the bone matrix there, the osteoid. Calcium finds its way in, and so it deposits itself. Right, those calcium salts deposit themselves along the osteoid, and it causes the crystals to deposit out and hardens the matrix. And so it traps some of these cells in that bone matrix, and so they convert into osteocytes. And that's what we see here, while these other osteoblasts keep doing what they were doing. So that's step 2. So step 3, okay, we're starting to get the formation of the early appearance of bone. So we call that bone woven bone, all right, also known as the primary bone. But it's not really good bone, okay? It's poorly organized. It's not going to be as strong as the secondary bone, all right? But it's not very good bone. When you say labeling those pictures, no, you won't be labeling the pictures. You won't have to worry about that. If you're, the lab exam, no. You won't have to be labeling the cells for the lab exam. So the woven bone is that initial bone that forms, right? Poorly organized. It's just our beginning model. All right, so what we'll see during this time as this woven bone is starting to form, then we're going to see the periosteum. All right, you know what that is. That's the covering to our bone. So the mesenchyme that's on the periphery or on the outside of this bone tissue, right, that mesenchyme is going to start to form the periosteum. So that's what happens in step 3. So you can see here with our formation of our woven bone here, again, there's no organization to it. But what we're seeing now is, okay, we've got the early form of the bone occurring. And then on the peripheries here, right, the mesenchyme starts to convert into or form periosteum. So you'll see we're going to get that inner cell layer occurring with all the different cells that come with that. And then we'll also get that outer fibrous tissue on the outside. But meanwhile, as this is occurring, you can see blood vessels are finding their way into this tissue, which is good because the blood vessels are going to carry the nutrients and the ingredients that we need for this process to carry on. All right, the 4th step, okay, is the replacement step. So our primary bone, the woven bone, gets replaced by the lamellar bone. And that's where we start to see, all right, the formation of compact and spongy bone. So the compact will be on the exterior portions, and then just internal to that, we'll see the spongy bone, right? And we'll see the trabeculae, okay, that little lattice scaffolding on the internal portion of the spongy bone there. So this is pretty much what we'll see when we're talking about our cranial bones, our facial bones, all right, a lot of these flat bones here. Remember that peanut butter sandwich I was telling you about? You're going to have, all right, the external layers of compact bone with a nice, all right, spongy bone filling in between the compact bone layers. And that's what we see over here in step 4. And so now we're replacing this poorly organized, kind of weakened form of bone, the primary bone, with the lamellar or secondary bone. So we started to get the formation of compact bone on the external portions of our bone. And then on the inside, that's where we're going to have our spongy bone. See all the trabeculae here? Okay, we have blood vessels. And then on the outside, we're going to have our periosteum. And so that is the formation of the intramembranous ossification. So when you're developing as a fetus, okay, and your skull is starting to take on that humanoid form, this is what's happening. That's what's happening. All right, that's intramembranous ossification. Now we're going to get into the endochondral ossification. I like the endochondral ossification. There's several more steps to it. But now we're going to learn how your bones, all right, for your arms and legs start to form. So it all starts off, okay, with our cartilage model. Remember what we said when we were learning about hyaline cartilage? It's the most abundant type of cartilage found in the body. Right? Your fetal skeleton starts off as a hyaline cartilage model. Right? But so that includes your upper and lower extremities, right, are going to develop using endochondral ossification. We're also going to see your pelvis, right, which is going to include your hips, your vertebra, and don't forget the ends of the clavicle there. So for the most part, we're going to see this in long bone development. So we're going to use the humerus, right, which is the long bone that's found in your arm in between your shoulder and elbow. So we're going to use that as our model here as we go through the steps, right, of the long bone development for the humerus here. So step 1, we start off with that hyaline cartilage model. So that means that that little miniature humerus has already undergone interstitial growth and appositional growth, all right, from those chondroblasts. So they have made, all right, the cartilage matrix, and they put it into place, okay, and this started, okay, anywhere between your 8th and 12th week. So we got a little mini humerus now, but it's made up of all cartilage. So that's what we see here. Step 1, okay, here's your little mini humerus, okay, so we have our cartilage model here with the perichondrium on the outside, which is nice because remember the perichondrium helps hold the shape for our mini humerus here with hyaline cartilage all on the inside. And it went through what we already talked about, the interstitial and the oppositional growth. All right, cool. So now we have a working model. Now we know what to start with. So let's move on to step 2. Now, earlier in this class, I told you we're not going to see calcium in the cartilage matrix. And now you're going to see why. Because here's what happens, okay? When calcium gets introduced to the cartilage matrix, it causes the process of calcification. And when that happens, I want to quote a movie, but I won't. Cells die. So when the matrix calcifies, the chondrocytes die. So that matrix, which was kind of semi-flexible, all right, I'm not going to say it's like wet cement, okay, because cartilage is not like that. But when we introduce calcium to that cartilaginous matrix, that calcification process, all right, causes the chondrocytes to die and the matrix to harden. And it hardens so much that the chondrocytes can no longer get the nutrients that they need. And if they can't get the nutrients, right, they die. And that's what we see here. All right, so as those cells start to die, we start to get holes inside the matrix. Well, that's good, because if we have holes, then our blood vessels can now infiltrate into those holes and start to spread out through our cartilage model here. And so with that, we start to get osteoblasts coming in on the scene. And what do? Blasts build. So the osteoblasts are going to start to build bone by secreting the osteoid. And here's the thing. They secrete the osteoid around that old, hardened, calcified cartilage matrix there. And so that's what happens. So this starts in the diaphysis, all right, right there in the shaft of the bone. So when this occurs, we start to get this structure called the periosteal bone collar. I'll show you a picture here. So just to quickly review, all right, during step 2, our cartilage matrix starts to calcify. What does that mean? Calcium infiltrates the area. It causes the matrix to harden so much that the cells, the chondrocytes that were already trapped in the matrix, they'll die because they can't get nutrients. And that produces holes in the matrix. And as a result, all right, the holes, you'll get these large holes there. As a result, blood vessels can now migrate into the cartilage matrix there because there's holes there and they can move throughout. Osteoblasts move in. They secrete the osteoid around the calcified cartilage shaft there, right, the remains. And we see, right, in the diaphysis of our little mini humerus, we start to get this structure called the periosteal bone collar. So that's what we see here in step 2. Okay, so right here in the diaphysis, right, calcium infiltrates. It starts to cause the matrix to harden, it calcifies. The chondrocytes die as a result of that. And now you have all these holes throughout. Well, blood vessels will start to infiltrate, bringing in osteoblasts. The osteoblasts start to secrete the osteoid on the old calcified cartilage matrix. And we start to get the formation of our periosteal bone collar. Now, again, this is all happening when you're still a baby, okay? When you're a fetus inside of mommy. All right, so this is going on before you're even born. All right, that's step 2. All right, step 3. Still focusing on the diaphysis, or the shaft of our little baby humerus there. And we're going to get the formation of what we call the primary ossification center. Primary because it's the first ossification center. And we talked about the process of ossification just a few moments ago when we were talking about the intramembranous ossification. Somewhat similar. All right, so we have the formation of this periosteal bud here, okay, that we see it extends in from the periosteum into the diaphysis there. And so as this periosteal bud starts to extend itself into the diaphysis, we're going to see the growth of capillaries all throughout the diaphysis, and we're going to see osteoblasts infiltrate that area and start to spread out. And those osteoblasts are producing that osteoid on top of that degenerated calcified cartilage matrix there. And so this is going to start to create bone formation all throughout the area. This will be through the diaphysis. So pretty much, all right, by week 12, the majority of the diaphysis is now bone. All right, in the process of weeks, this goes from a cartilage matrix into now a bone matrix. And so it starts in the middle of the diaphysis and it extends towards either end of the bone. If you recall the names of those structures, those are called the epiphyses. And basically, what we're going to see from here on out is bone is going to come in and it's going to replace the calcified, degenerated cartilage. So it starts off in the diaphysis. So that's what we're going to see here in step 3. Okay, we already saw it starting here with step 2, and now it's going on a grand, on a larger scale here. So blood vessels have infiltrated in, osteoblasts have infiltrated in, and it's just using that old calcified cartilage matrix as a template, and it's going in and replacing all that calcified, degenerated cartilage matrix with bone tissue. And it starts from the center and it works its way towards the ends. And this is what happens by the 12th week. Most of the diaphysis now is turned into bone. Okay, that's step 3. Step 4. Now, keep in mind though, I'm going to move on and talk about these secondary ossification centers. But everything that we just talked about with the primary ossification center, all right, that's still ongoing. Okay, but by now, when the primary ossification center is really is kicked into high gear, now our secondary ossification centers are going to start to develop in the epiphyses. So same scenario, we're going to see, okay, that hyaline cartilage that used to be there is going to calcify. And as a result, the chondrocytes die and that tissue degenerates. So we start to get hole formation occurring. Well, blood vessels infiltrate that area, and now osteoprogenitor cells are going to enter into, okay? And we know what osteoprogenitor cells do. Okay, they're going to produce the osteoblasts, and it's going to build the bone. So the osteoblasts start to secrete the osteoid on the degenerated calcified cartilage matrix, and we start to see bone displacing the cartilage. And this is going on in the epiphysis. Now, meanwhile, our osteoclasts get on the scene, because now we're going to see some resorption of some of that new bone matrix that we just laid down, because it's not perfect yet. Okay, it's woven bone, or we haven't gotten it to that better quality bone, right? So we're going to start seeing resorption of that bone matrix, but in the diaphysis, we are going to start to see the formation of our medullary cavity. All right, so here, this is what's going on when you're a baby, okay? So you'll see, all right, a lot of the diaphysis is now osseous tissue here. All right, we're getting our secondary ossification centers are occurring, all right, in the epiphysi. All right, and now we'll even see the formation of the medullary cavity, because the osteoclasts are going gangbusters in here, and they're starting to hollow out, all right, the diaphysis here of the bone. All right, so again, this is going on in a baby, newborn. All right, last 2 steps. Step 5, rinse and repeat. Basically, step 5 is telling you, all right, we're going to get rid of all of the cartilage in our bone except for 2 areas. All right, the articular cartilage on the ends of the epiphysis and in our growth plates, or the epiphyseal plates. So if you're cartilage and you're not in the articular cartilage or the epiphyseal growth plate, then you're getting replaced by bone. And this goes on for many years. Through childhood development, this is constantly happening. So we're seeing now, all right, pretty much all of the cartilage that was in the epiphysi, all right, is gone, and it's been replaced by bone. All of the cartilage that's in the diaphysis, again, is gone and replaced by bone. So the osteoclasts are still working on hollowing out that medullary cavity, because remember, as you grow, your bone gets longer and it gets thicker. Okay, so we're constantly trying to make the medullary cavity bigger. The only areas that you're going to see cartilage remain is going to be in the epiphyseal growth plate here and where there's articular cartilage. Those are the only places. And so this is going to go on, all right, throughout your childhood and throughout your adolescence. Which brings us to step 6. And so that lengthwise growth will continue until you're done growing and the epiphyseal growth plate, all right, ossifies, which means all the hyaline cartilage that was in the epiphyseal plate is now turned to bone. There's no more cartilage there. And so you will no longer gain any more lengthwise bone growth. So we'll see a lot of this step 6 is going to be occurring, all right, between ages 10 and 25. Okay, and then obviously now it can vary. It could be 26, 27. Some people could still grow at that point. Okay, but this will all continue on until eventually the epiphyseal plate ossifies and we have no more, all right, hyaline cartilage. And that's what we're looking at here in our last picture. All right, so the latter portion of your teenage years or your 20s, this is what your long bones will look like. We have a nice predominant medullary cavity filled with tons of blood vessels, okay? We no longer have that growth plate there any longer, okay? It is all ossified, and so the bone will no longer get any longer. But the only place that you'll have hyaline cartilage will be on the ends of the bone where there's articular cartilage. I suggest that if you're not quite sure, kind of review that, go over that material there. Again, it can be somewhat, there's a lot. Walk yourself through the steps, watch the video. I recommend that you just read these figures 7, 11, all right, memorize this first so you have a general idea. Okay, and then go into the more detailed explanation of it. That's a great question, David. Part of it is going to be, I mean, there's several possibilities with that. One is, you'd have to be smoking quite a bit, okay? But the smoking is going to affect the vascular supply first and foremost. But also some of the chemicals that are put into cigarettes are going to mess up your hormones, which is actually, this is a great question that's going to kind of lead us into, because we're going to talk about hormones shortly. We might start them a little bit today, right, and then finish it up next class. Right? But the smoking will mess up with the blood supply and it will mess up the hormone productions, which we'll get into, and it will throw those out of whack and cause some of those issues that you're talking about. Bone growth and remodeling, right? This is going to start off as an embryo, okay? And it'll continue. Right, well, the remodeling portion will continue throughout the rest of your life. Right, the bone growth will stop when puberty ends. Okay, so when we're talking about same thing we saw with cartilage, the length, increase in the length of the bone, that's the interstitial growth. Right, growth in the width of the diameter of the bone, that's the oppositional growth. Okay, so the interstitial growth is what we see at the epiphyseal growth plate. We'll talk about that in a moment here. Basically, when we're talking about the growth plate there, you've got your cartilage cells there, the chondrocytes, and they're obviously going to be making that the cartilage matrix there. And then the osteoblasts are going to come in and they're going to produce the bone matrix. So the osteoblasts are going to be on the diaphyseal side of the growth plate, whereas the chondrocytes are going to be on the epiphyseal side. And I'll show you a picture here. So basically what will happen is the cartilage is going to get pushed toward the epiphysis, We're going to talk about the different zones of growth here in the epiphyseal plate. All right, so your growth plate or the epiphyseal plate. Okay, this is going to pretty much maintain its thickness as you're developing during childhood. As you get closer to your skeletal maturity, all right, it will start to slow down. All right, but we'll see a significant increase in the osteoblast activity. All right, and so when we see the osteoblast activity increase significantly, we're starting to see the ossification of the bone, right? And then eventually, all right, the cartilage production will decrease and be overtaken by the osteoblast activity to eventually where it overtakes all of the cartilage. All right, so let's talk about bone growth when we're talking about interstitial growth. That is going to be lengthwise, how you get taller. And so this is going to require us to focus on the epiphyseal plate here. So there's 5 zones. So I'm going to start off, all right, by talking about each zone here, and then I'll show you a quick picture. So the first zone, this is going to be closest to the epiphysis. This is the resting cartilage zone. All right, so we have all these chondrocytes scattered throughout the matrix here. All right, so this is where we're going to see when you're looking at this tissue under a microscope, all right, that tissue is going to look like mature hyaline cartilage. So the chondrocytes are not doing anything. Now, in the second zone here, the proliferating zone here, the chondrocytes start to divide. And we saw what happened before when we were talking about interstitial growth in the cartilage. So this gets applied here, okay? So the chondrocytes divide. Where there's 2 chondrocytes in a lacuna, all right, they start to produce new matrix and push away until each individual chondrocyte has its own lacuna. All right, but in this area here, we start to get the lacuna to line up, all right, and they look like a stack of coins on top of one another. All right, so we'll see tons of chondrocytes in this zone here stacked on top of one another in their lacuna. All right, so these columns or these stacks are going to be parallel to the shaft of the bone. So once we get these brand new cells, well, what happens after you're born? You start to grow. So in zone 3, we start to get the hypertrophic change. What does that mean? We get an increase in the size, okay? So the chondrocytes are no longer dividing. They undergo hypertrophy, which means they just get bigger. All right, so when they get bigger, they're going to take up more space. But unfortunately, all right, they get moved on to the next zone, and this is where they start to die. So they don't really live too long of a life here. Okay, but this is the zone in which we start to harden the cartilage. So the chondrocytes undergo calcification. What does that mean? All right, that means the matrix starts to harden. And by doing so, that kills off the chondrocytes and they die. Which brings us to our last zone, right? The zone of ossification. And in this zone, all right, the walls of the lacuna start to degenerate and break down, and we get our capillaries, our blood vessels start to infiltrate those areas and bring in our osteoprogenitor cells, which are then going to build our new bone matrix on top of the old, dead, degenerated, calcified cartilage matrix. Same stories we saw before. So here you can see, okay, our 5 zones here. The top zone, okay, the chondrocytes aren't doing anything. And then they start to decide, all right, we're going to start to divide, and they undergo that mitotic division, and they rapidly undergo that division. They start to line themselves up in their lacuna like stacked coins. And so in this zone, we're just seeing a rapid proliferation of the cartilage cells, the chondrocytes, as they divide. Well, then what happens here in the third zone, they start to grow up and get bigger. So they undergo hypertrophy. And then that pushes those cells down into the next zone. And unfortunately, calcification starts to occur in the matrix. That kills off the chondrocytes. As they degenerate, it leaves these holes here. And then that moves us into the 5th layer, where our capillaries infiltrate the area, bring in the osteoprogenitor cells, and the osteoprogenitor cells produce the cells that are going to build the new bone matrix on top of the old calcified cartilage matrix. And that's how we get our interstitial growth. So we really see the majority of the interstitial growth and length here in these two zones. The proliferating cartilage, that's where the cells are mitotically dividing. And then zone 3, the hypertrophic cartilage zone, in which the cells are actually getting bigger. So as this is occurring, these processes, it pushes that first zone, the resting cartilage zone, towards the epiphysis here. And this goes on throughout your childhood, throughout adolescence. It starts to slow at the latter end of adolescence, right? And eventually, right, no more chondrocyte division occurs. That means no more hypertrophy. All those cells get overtaken by the calcification of the cartilage matrix, and our bone cells come in and take care of business. All right, that brings me to the last part that I want to talk about today, and that's the forensic anthropology. This is, and there was a show, I think it's called Bones. I've never watched a single episode of it, but I'm somewhat familiar with it, right? But basically, if we want to be able to tell, right, the age of a skeleton, right, one of the ways that we do it is that we look at, right, the growth plates, if there are any. And so in a younger skeleton, right, we'll actually be able to see somewhat of a separation between the diaphysis and the epiphysis. Whereas in an adult skeleton, that is all fused together. And so we're able to determine, right, what has occurred. If it's a complete union, all right, between the epiphysis and the diaphysis, right, then we know it's an adult skeleton. All right. But if we have an open or partial union, then that helps us to figure out, all right, or close approximation as to when that person died. So they'll use different ways, because we know that certain growth plates will close at certain ages, and some will close earlier or later than others. All right, I'm going to stop here, all right, because I smell some food cooking downstairs. Just kidding. I am going to stop here only because it's a good place to stop. So